I have to be careful to say least material condition and not minimum material condition, because then they're both M's and it gets quite confusing. So at least material condition, I'm gonna say I want, let's say no more than 1 millimeter slop, right? So I want less than 1 millimeter of gap between the two. So I've either know that from experience or I've done some analysis and decided that's how loose I'll let my part be. Then it's just simple geometry again. So I'll say my 10.5 millimeters for my hole plus the upper tolerance of the hole should still be, let's see here. So that size minus my 10 millimeters for my shaft minus the lower tolerance should be less than or equal to 1. Right, so I'm saying here's my hole as big as it can get, and subtract that by my shaft as big as it can get, and it should be less than 1. And that'll satisfy my condition. So again, I'll have 0.5 millimeter plus HU plus SL is less than or equal to 1. So I can say HU plus SL should be equal to half. And so in this case, again, I have one equation, but two variables. So this time I'll just say we can split them. So we can let HU equal 1/4, and that will let SL also be 1/4. So I can go back and check them again. So if I let my shaft lower be 0.25, then my shaft would be 9.75. And if I let my HU be 0.25, that's 10.75, subtract those and I get 1. So that's my boundary case, right? So it's not very complex when you have something like this, but if we go and look at the Lego example, right? So let's say we have just a 4-brick Lego. And so you have this one and a negative of this one, right? As you're putting them together. Now you need these 4 to have the distances correct and the radiuses correct on all connections. So your geometry just, even though it's still simple geometry, you have a lot of things to line up now, right? So this is where gauges come into good use. So instead of going through and checking every one of those dimensions on these parts with a pair of calipers, you can create a functional gauge where you can just stick the brick in. If it sticks, it works. If it doesn't stick, it doesn't work. Okay? And you can put those gauges on the boundary conditions to check them just with a simple functional check. Does that make sense to everybody? It's a lot simpler than individual inspection methods. But those are some of the really widely used means of checking tolerances. Does anybody have any questions on all of that? Okay. Geometry, pretty simple. Okay. So like I said, I come from a mechanical background. You're saying, you just talked for half an hour about prints and tolerances, why do I care? Well, this is a schematic for a PCB. There's a title block, there's a bill of materials, there are dimensions, geometry. So you guys will work with this stuff too. Any industry that you're in, if you're doing it in a technical field, you're going to have written documentation about how your design works. And they all follow very similar rules, okay? So understanding how those work and how to create them is very important because you want to control your design, you don't want someone else controlling it. Oh no, I lost my audio.
Prove that you have the unlocked potential to be. Doing? We are entering your mind to prove that you have the unlocked potential to be a master builder. Giant.
Whoa, are we inside my brain right now? Hey, I must be smart.
I'm not hearing a lot of activity here.
I don't think he's ever had an original thought in his life.
That's not true. For instance, one time I wanted to have a bunch of my friends over to watch TV, not unlike this TV that just showed up magically, and not everybody can fit on my one couch. And I thought to myself, well, what if there was such a thing as a bunk bed, but as a couch? Introducing the double-decker couch. So everyone can watch TV together and be buddies.
That is literally the dumbest thing I've ever heard.
Please, Einstein, let me handle this. That idea is just the worst.
Okay, so while prints and tolerance analysis may not be the most interesting subject, I want you all to become master builders, and it's a step along the way. So you now have a print and you have tolerancing, but it's still just the beginning, right? So now you have your part specified and you want the part to be made, right? So a few things that you need. First would be CAM, right? So those of you who have worked in the AFL, and you go down and bring them your model, and you're like, I'm ready to make something. The first thing they do is schedule time for you to create your CAM, right? So this is computer-aided manufacturing. So it's going to go through and set the steps that the machine follow to produce your part. A couple other things that you'll have in industry when you want to make something are called a router and a bill of materials. And the easiest way to think of these are like a recipe. Probably none of you have ever cooked anything, but in a recipe you have at the top a list of ingredients that you should buy. Okay, so it'll tell you you need, butter and flour and whatever else you might need to make what you're going to make. So it's the ingredients list that you need. So your bill of materials is the ingredients that you need to make the part. The router are like the steps of the recipe. Okay, they tell you what you need to do to make this part. So it'll say, step 1, go to a 5-axis mill and run this program. And this is the training you use and the standards you use, and it will specify everything you need to do at that step. And then step 2 is you go to another machine and do a secondary operation, and then you go to surface finishing and packaging and labeling, and it'll go through every step you need to get this part through and out the door. How many of you have made a part on one of these before? 3D printer of any sort? Fair number of you. So there's an epidemic in the student mindset that this is how parts are made, but I doubt that any of you own anything that was made on a 3D printer, right? So in industry, we don't 3D print much. You might make a rough prototype just to check and see size and feel, things like that. But this isn't how parts are made. Parts are made through things like this: casting, molding, machining, stamping, forging, welding, and brazing. Amongst a lot of other things. Again, these are kind of mechanically oriented, but any discipline would have its set of traditional manufacturing methods that are good for making mass-produced parts. So if you don't know, casting is a method of getting a overall shape and usually a piece of metal. Okay, so you'll have a mold, you put molten metal into it and you get out a shape. There are several different kinds of casting. Molding is usually associated with plastic, so those Legos are molded. I think they use injection molding for those. Machining is a method where you take a block of material, it's subtractive, so you're cutting out material to create an end shape. If you've been down in AFL, most of what you do down there is machining. Stamping is a method of shaping metal with a large press that goes over a mold. So old auto bodies were stamped before they were plastic. I don't know how they may still be stamped, but you have forging, welding, and brazing are some additive manufacturing methods. So these are some of the things that you'll see real parts being made this way. So not to take anything away from 3D printing, I love 3D printing, but just be aware that I made a part when I was in college using the 3D printer is not the same as manufacturing a part. I'll give you a. Let's skip this. I'll give you 5 seconds of it because it's kind of neat. Or maybe I won't. I skipped it. You can do it? No? Okay. And then, so then you've made a part. I'm sorry, I'm running short on time. And then you want to check the part. Okay, so we talked a little bit about tolerancing. There are a number of ways to check parts. So some of the most simple ones, if it's 10 feet long, if I'm doing a woodworking, I'm building some bookshelves, I'm going to use this guy. It's a tape measure, right? So I don't care about my tolerance more than, say, a 1/16 of an inch. This is a great tool to use. If I want to have more precision, I might use one of these. These are called calipers, or I could even use micrometers, which do even smaller increments, okay? So these would get me down into 1,000th of an inch. And 1/1000th of an inch is pretty precise. If you're ever making a part that's less than 1/1000th of an inch, you'll be either in a really specified industry or you're doing it wrong. Okay, so if you're making a precision valve maybe, or if you're working on space shuttle, things like this, you might be under 1/1000th of an inch, but most parts are going to be around that range at the very smallest end. Okay, you can make some very precision parts that way. Getting beyond the individual part, so if I'm measuring this shaft, a set of calipers would work really well, right? I can just clamp around the shaft and know how big it is. But if I'm doing something more complicated, like the body of a car that has a lot of geometry to it, I'm not going to measure it that way. I might use something like a CMM right here, although that would be a very big application for a CMM. But what this does is takes a stylus and it touches a big cloud of points, okay? And then it has software that maps those points together to build a surface. And then you can compare that surface in your CAD package against your model to see if the surface is correct. So instead of taking one dimension, like a width or a length, you're measuring a whole surface. Likewise, things like this, you can do a white light scan or a laser scan. You can build a very precise point cloud and measure that surface against your model. So those are some of the techniques you can use. I mentioned a little bit gauges. So people in the quality profession spend a lot of their time making gauges. So this is where you want to be able to take a whole part and say, yes, it does or does not work, instead of measuring those individual dimensions. Okay? So some engineering roles. I mentioned that nobody in industry hires mechanical engineers. These are just a couple of the, or I guess a few of the very common actual engineering professions or roles that you would have as an engineer on a design team. Beyond the design process, there are many more. So you have process engineers and things like that that do like industrial engineering type jobs. But some of the core ones you'll see pretty much everywhere are design engineers, and really their job is to make prints. So you're going to work with the customer, do the kind of things that you guys are used to doing in EPICS, right? So you're going to meet with your partner, your community partner, your customer in industry, say, what do you need? Come up with the ideas. So you get to do a lot of the creative work. And this is what I did in industry. And it's a lot of fun. But once you have those, then you want to get into manufacturing engineers. So their job is to make parts, okay? So they're not the operator who's making the part, but they create the structure for that. So they might do those CAM programs, things like that. So you're looking at tooling, machine programs, training operators, things like that, okay? So there are a lot of engineers in these roles. And then lastly here, we'll talk about quality engineers. So when we just talked about checking parts, they do that role, okay? So these people work together very closely because the design engineer wants to make sure that the part is made correctly and work with the quality engineer on how to do that because they have a lot of expertise. So, you know, in design teams, these people interact a lot. So just because you're a quality engineer doesn't mean you don't have any input into the design. You do, because you want a design that can be checked, right? So you want a design that you can verify as a good part. So one idea, design for assembly and design, yeah.
So just hypothetical question real quick. So if you have like a design guy, manufacturing, and quality guy, and they all kind of have like a different idea about how to do like a certain aspect, which one would have like the most weight as far as like decision, like, you know?
That depends on the culture of the company. So I came from the medical device industry, which has large profit margins. So the development engineers have a lot to say because you're looking for novel designs, right? In industries that run tight margins, a lot of times the manufacturing or quality engineer would have more say because a part that costs $1.03 versus a part that costs $1.05 is a big deal, right? Because if you're making 10 billion of them. So I worked in a small volume, high profit margin industry where ones that are the other way around, where you make a whole lot of something but at a small margin, it can go the other way around. Does that make sense? But I would say in general, there's a lot of respect between these groups. So, you know, I worked with a lot of manufacturing quality engineers who provided great valuable insight into parts, okay? So that's one thing I want to talk about here. So traditionally, I should say, in the past, and this has been moved away from a lot, the development engineer would work with the customer, maybe with marketing, and create this design and then say, here you go guys, make this, and throw it over to the manufacturing engineer. And that's a really terrible way of doing it because development engineers don't usually know a lot about how parts are made, especially how they can be made in a cost-effective way, which, while not very interesting or sexy, is really important, okay? Because we want to work for a company that will stay in business, so we want them to make money. So this idea of design for manufacture comes from saying, we're going to think up front about how we can make this part so that it can be manufactured well and in a cost-effective way, okay? So you're looking at things like minimizing part count. I guess, so this is for assembly specifically. So these are related. Design for manufacture is making that one piece, and design for assembly is putting them together, but they're both for the same purpose. So minimizing the part count, thinking about your assembly workflow, minimizing the chances for errors, right? So my handle here had a lead in on one side, had a chamfer on one side, and not on the other. So that would give you a visual indicator if that's the side you put it in. But you could still put it on backward. So I could have designed that in a way that would prevent you from doing that with like a key in or something. And when you're doing thousands and thousands of parts, being able to assemble quickly without thought so you can't do it wrong is really important. And it saves a lot of money and time. Design for manufacture, you think about using stock parts. So if you can buy a screw instead of making a screw, it's really cost effective because it might cost you 2 cents to make it and $12 to build one. So I actually personally did that wrong. I think my first year as an engineer, I was designing a set of instruments for revision knee surgery. So this is, you've had a knee surgery, you've taken it out, and you're putting a new one in. And we had a thread that had an English thread with a metric head. There was no reason to do that. It was just inexperience, and no one in our team caught it. So we ended up making these like $6 screws when we could have bought them for 10 cents if we had just switched the thread. So those mistakes happen. Learn from other people's mistakes. So design for assembly and manufacture, get those manufacturing people in early on in the process and respect their opinions because they will be able to help you avoid things like that. I know I'm out of time. So a quick example of that. This is designed for assembly and this one is not. So if you came in with this design, there's nothing that the manufacturing person can do to make this any cheaper. But if you had talked to them up front, they may have told you you could make it like this with a bending process, and now this thing assembles in one step, right? So this part would be a lot cheaper in the long run than this part, even though this may have been more straightforward to design. And you can see in the phase of product cycle, so this blue line is incurred cost. So this is cost you've actually spent in your project. And the red line is committed cost. So this first section is the concept phase. So you've spent very little in the conceptual design phase because you've just maybe made rough prototypes, but you've set yourself on a path to account for 60% of your overall spend on the project, because once you've set on a design, you can't go back and create a manufacturing method that will make that part any cheaper, okay? So say if you're doing casting, and you've designed a part that can be cast, that part might cost $1 a piece. But if you design that part so it couldn't be cast from the very beginning in the concept, and you have to machine that part, it might cost $50 a piece. And there's nothing that your manufacturing engineer can do to get that $49 back, okay? So getting those people, your manufacturing quality people involved in the conceptual design phase can account for a 50% reduction in cost. Okay, does that make sense to everybody? So this is why we want to do the design for manufacturing idea. It won't matter too much in EPICS, but it's good to understand when you get through. So trust those people in those groups that you work with. We'll skip the exercise because we're out of time. But if you're bored, it's this one. So try and put 2 pieces of Lego together. It'll be challenging. You'll get frustrated. You'll not want to do it anymore. And then you can send me an email and tell me how frustrating it was, and I'll agree with you. Okay? That's kind of the point of the exercise, is to see it's hard. All right?